Okay, good. So this is a problem I would say is, so it's a graph problem. Sorry. Yeah. Sorry for that. I'm Victor Verdugo. So ENS, UCHILE. Okay. Good. So the graph problem is simple, in fact. So I get that most of you are familiar with perfect matchings and factorization. So the problem is the following. So we say that a graph G is one factorizable if there is a perfect matching decomposition, okay? A perfect matching decomposition. Good. So if we can find such a decomposition, then we have a one factorization. But the thing is the following. So there are some graphs that are not one factorizable, but are fractionally one factorizable, okay? In what sense fractionally? In the following. So let me write an IP of this thing, okay? So the IP could be the following. So ym is just a variable saying one if the matching M is in the decomposition, 0 otherwise, okay? And then the IP is the following. So I pick every edge in the graph, and it has to be covered, okay? So the following, right? So it's EM. Sorry, let me put here EM if M is in the decomposition and the edge is in the perfect matching. And then I want to cover every edge. Okay, this is the whole thing. So I want to cover every edge. So this is over M, such that the edge is in the matching. And then let me assume something more. Let me assume that the graph is regular, okay? So the degree is regular. And then we know how many matchings we are using, in fact, right? So we know how many. So it's just the degree, right? So so now if I sum over M, right? How should I write this thing? Okay, let me put it like this. So we are using exactly degree perfect matches. Okay, good. And the thing is the following. So there are some graphs for which we can find such an integer decomposition, but there are some others where this is not possible, but fractionally it is. Okay, so let me give you an example. So just the Petersen graph. Okay, so in the Petersen graph, we have this. So you can check by hand easily that you cannot find a one factorization. Okay, there are 6 perfect matchings. Each edge is covered by 2 of them, but you cannot decompose the graph into perfect matchings. But it is fractionally. Why? Because every edge can be covered by 2 perfect matchings exactly. Okay, so you can find that, in other words, you can construct a distribution over perfect matchings in a way that you cover every edge. Okay? So this is an example of a fractionally decomposable graph, but not integrally. Okay? Good. So now the first question is, and here is why I think that people more in graph theory can be extremely helpful. I don't have many examples of such a graph, in fact. So this is a bit surprising. I mean, I have looked a lot. Maybe I have looked in the wrong literature, but I have no many examples of graphs like this, okay? Not being integrally, but fractionally decomposable. So this is on one thing. Let me put it like question 1, like the very preliminary question. Find examples, right? find examples. But the real question, question 2. So this thing has an implication. So finding such an example has an implication in combinatorial optimization. Okay. So there is other problem, which is the following. So maybe some of you are also familiar. So it's scheduling identical machines. Okay. And let me say in this way, if you find an example of such a graph, then you have a gap instance for this problem, okay? And what is a gap instance? Is the following. So in this thing, so just tell me if I'm taking too long, okay? So, but let me make it brief. So in this problem, you have machines, so which are just, let's say, bags. Okay, so I have bags, and I have jobs. So I have a set of jobs, J. I have a processing time for each one, which is just number, okay? So just an integer number. And I want to pack them all into the bags, okay? So I will put, imagine rectangles of this size with height 1, and I want to pack them here, okay? So they will look like this, like this, like this, like this, and blah, blah. Okay? And there is a number here, which is, let's call it T. And I would say that T is a good number if I can pack everything within T. Okay? If I can pack everything within T, then this is a good number. But again, so this is for packing integrally, right? But you can answer the question again fractionally. Can you pack everything fractionally? Then, of course, you need less, right? Let's say if I need 100 to pack integrally, then I need at most 100 for packing fractionally, right? Because again, now for every job, I have a distribution over the machines, right? Okay, let me tell you the following. If you find an example here, you can construct a gap instance for this thing. And the theorem we have so far, which is in a way weak, but is the only thing we know. And this is it is a bit surprising to me because I can imagine that you can find such a better example, right? So more complicated. So this is in a way the simplest one. So if you put the correct, okay, and the connection is just imagine every bag as a perfect matching. Jobs are as edges, right? So here you want to cover everything exactly once. So here you want to pack everything exactly once. So how to pack a single machine is just a perfect matching here. So then the mapping follows, right? So in that way. And the theorem is that the number, let's say the T integral, okay, the T integral here versus the T fractionally, the T fractional, okay, is at least 1 plus 1 over 1023, okay? And the magic number comes from putting the right weights here. So you have to then construct the processing times. But more important than that is to find a good example, okay? So if you have an example like this of a fractionally decomposable graph, but not integrally, then you can construct a thing like this. And for me, at least, it would be very interesting because this is the best we know for the gap in scheduling. But my guess is that is way more, okay? So let me tell you that the upper bound is 2, in fact. So this is at most 2. So we have a large gap in between, right? This cannot be the right answer. So this is what I'm saying. I don't think it's the right answer. So this is what you obtain from Peterson. But if you have other graph, then you might construct other graph, okay? Hope this is clear. So, yeah. No. This is what I told you in the beginning. So, might be that I'm looking in the wrong literature, but I haven't found. I mean, if even a simple infinite family of such a graph would be interesting, right? So, no. And yeah, so this is the question. Yeah. So, well, after that, then there are other questions that I'm also interested in. But I think that in the beginning, this is like the question. So then all the other depends on this. So yeah. 2 is an upper bound. Okay, so 2 is an upper bound. It basically comes from the fact that if you have t fractional, you multiply it by 2 and you can prove that you can pack everything. So this is the thing. Exactly, exactly. Yeah. Exactly. And for me, I don't think this is the right answer. It's just too specific, it's Peterson, okay? So it's really, maybe I can tell you later how you construct the 1023, but it's just picking this graph, putting some numbers, and you get the, yeah, so. Yeah, okay, so I don't want, yeah, so actually I'm skipping a bit here. Here you can write a linear program, okay? So you can also write an IP. Yeah, so it's identical machines, okay? So they are all equal. So you want to place those jobs in the machines, okay? And so what you look for in the beginning is for the minimum t. So for the minimum t in a way that you can pack everything integrally, okay? So this is called the makespan. What is the minimum t in a way that I can pack everything? And fractionally, it just relax the condition of packing integrally. Now you can pack fractionally. So I pick a job and I have a distribution over machines and I schedule according to that, right? You can write an IP. Again, it looks, and this is the key thing, in fact. So it looks exactly like this one, in a way. And then the gap, more precisely, is how different is the minimum t for which the LP, so the relaxation of the IP is feasible, versus the minimum t for which the IP is feasible. Okay, so this is the gap notion here. Okay, so here the gap notion is just whether I can pack fractionally or not in the graph setting. Here it's a bit different, but I can show you that from here you can translate to here. No assumption. So it's just what I said. Identical machines, I want to pack them all. It's the most simple scheduling problem. Yeah. No, okay, so the thing is that the IP you're, okay, yeah, thank you, Dan. Yeah. So the IP you write is how you pack a single machine, okay? It's not the IP on whether I send a job to a machine. So you have variables YIC, which is I pack machine I, okay, pack machine I in, let's say, subset of jobs in C, okay? So let's say you say, I will pack job 1, 2, 4, and 7 in machine I, and then C would be 1, 4, what did I say? 1, 3, 4, and 7, okay? So I pack all these jobs in that machine. And this is a variable. So then the constraints are just, I want to pack exactly once every machine, and every job has to be in some of this C. Okay? This is the IP you write. Okay? And for that IP, you can prove that the gap is at least that, and it's at most 2. Yeah? So you got the... No? Yeah, I think so, yeah, offline. But this is just the idea. So how to pack a single machine. So it's a subset of jobs, what the C represents, okay? Not a single job. So I say I will pack machine I according to this subset of jobs. Everything, so all those subsets has to be a partition of the set of jobs, and every machine receives a single subset. It's just that. It's just a partitioning problem. So maybe it's simpler to imagine as a partitioning problem, okay, with a packing constraint. No? Okay, maybe we can talk offline. Okay. Yeah?
Thank you, Victor. So I think we have time for one more problem, if anybody's interested. Yes, sure.